Welcome back to the deep dive. Today we're tackling, well, one of those really nail-biting challenges in software engineering. How do you confidently deploy updates to critical high-scale streaming apps, especially those built with Apache Flink?
Oh, yes, Flink. It's incredibly powerful, famous for its exactly once processing guarantees, which is fantastic for things like financial data, where every single record counts precisely once.
Exactly. But that power, it hides a pretty serious risk, doesn't it? A faulty new build could just silently start corrupting data streams at massive scale, too. And you might not even notice until it's way too late. It's like this ghost in the machine scenario, a real potential nightmare. So the big question is, how do you find that ghost? How do you ensure both speed and safety in your Flink deployments? That brings us to our focus today. Automated Canary Analysis, or ACA. Think of it as a smart way to deploy.
That's right. Our mission here, really, is to unpack how ACA uses this uh, potent mix of observability tools and smart automation. The goal is to make those Flink rollouts self-validating, to catch problems, prevent silent data corruption, and slash the time it takes to spot issues.
It's about building confidence right into the deployment pipeline, yeah.
Precisely. Turning that risky venture into something reliable, almost self-healing.
And we'll see how this automation can actually prevent major incidents by catching things super early.
Okay.
Let's really get into that core problem first. Flink's exactly one's thing. It's a superpower, no doubt.
Absolutely.
But it means if you deploy a bad version, it's not just about crashes. It could be much worse, much quieter.
Right. It could be subtly corrupting data,
Hmm.
maybe small calculation errors, incorrect routing, stuff that's hard to spot immediately.
And at Flink scale, that can mean huge amounts of bad data before anyone notices, maybe hours, even days later.
hmm Downstream systems start failing, and then you trace it back. A nightmare. That's the specific challenge ACA tackles head on. And automated Canary analysis is the direct answer here. It lets you test the waters, essentially. You expose that potential new version, the Canary, to just a tiny slice of your live production traffic.
Like the old canary in the coal mine analogy.
Exactly like that. A small, very closely watched test. Then, the system automatically looks at how that canary is doing its performance, its health metrics. Based on that analysis, it makes an intelligent call. Do we promote this new version to take all the traffic, or do we hit the brakes and roll it back immediately?
Before any real damage or data corruption happens.
That's the key. It's absolutely fundamental for data integrity and keeping things stable in these high-stakes streaming environments.
Okay, so this isn't just one magic tool. You mentioned a combination. This sounds like a pretty complex setup.
It is comprehensive, yes. Think of it as a reference architecture, a sort of symphony of specialized tools all working together.
A symphony, I like that. So multiple instruments playing their part.
Spot on. Each component has a very specific job. Let's start with deployment. We often use Argo rollouts. It's built for Kubernetes and manages sophisticated deployment strategies like blue-green. It spins up both your current stable version, the baseline, and the new Canary Flink jobs. Crucially, with distinct labels.
So you can route traffic specifically to the baseline or the canary for that isolation.
Precisely. That isolation is critical for a clean test. Then for metrics, we lean on the Prometheus operator.
Not just Prometheus, but the operator. Why the operator specifically?
Well, the operator makes managing Prometheus within Kubernetes much easier. It handles auto-discovery, configuration, scraping, so it automatically finds and scrapes metrics from the Flink job managers, task managers, even from Pyroscope, which we'll get to.
Okay, high-resolution data.
Yeah, typically 10-second resolution. It becomes the central hub for all that quantitative data, CPU, memory, latency, throughput, you name it.
Got it. What about logs? They're crucial too.
Absolutely. For logs, we use Grafana Loki for centralization. But the really clever part is pairing it with Loki Canary.
Loki Canary, what does that do?
It's a small helper component, often run as a daemon set, so it's on every node. Its job is to check if the logging pipeline itself is healthy. It sends test log lines and verifies they arrive in Loki correctly, so you know if your logs are actually reliable.
That's smart. It checks the checker, essentially.
Kind of, yeah. It ensures you're not missing logs, which could mask application problems.
Okay, metrics, logs. What else is in this symphony?
Continuous profiling with Pyroscope. This is a really powerful addition. Pyroscope constantly profiles CPU usage and Java heap allocations within your Flink tasks.
So not just how much CPU, but where the CPU time is being spent.
Exactly. It gives you deep insights into performance bottlenecks or excessive memory churn that standard metrics might miss. And the neat thing is, Pyroscope exposes these profiling insights as metrics that Prometheus can then scrape and use in the analysis.
Right, closing the loop. So we have deployment, metrics, logs, profiling. What puts it all together? The decision maker.
That's the ACA judge. This is the brain. It could be a Flink batch job itself, or maybe a Python script. Its job is to fetch all that time-aligned data from Prometheus and Loki, run statistical tests comparing Canary and baseline, and calculate the final Canary score.
The score that decides the fate of the rollout.
Yep. And finally, control. This involves Alert Manager and the Argo Rollouts API. Alert Manager watches that Canary score. If the judge calculates a bad score, Alert Manager fires an alert. That alert then triggers an action via the Argo Rollouts API, usually telling Argo to either promote the Canary or abort the rollout. It closes the automation loop.
Okay, that architecture makes sense. Argo for deployment, Prometheus for metrics, Loki for logs, Pyroscope for profiling, the judge for analysis, and Alert Manager Argo API for control. That's quite the setup. But how do you actually get the data into those systems? Especially the Flink-specific stuff. It starts with instrumentation, right?
Absolutely. Garbage in, garbage out applies here too. You need good data. For custom Flink metrics, Flink itself provides APIs. Your application code can expose its own critical KPIs. Conceptually, you use something called a metric group in your Flink code. You can add, say, a gauge for record latencies.
Like the processing time for the last record.
Exactly. Or a meter for records per sec to track throughput. Then you configure Flink's Prometheus reporter. That reporter exposes these custom metrics on an endpoint that Prometheus knows how to scrape.
So you're teaching Flink to report its vital signs in a way Prometheus understands.
Precisely. Now for Loki log health, remember Loki Canary.
Yeah, the log path validator.
Right. So Promptail, which is Loki's agent for collecting logs, scrapes the logs from both Loki Canary and your actual Flink application pods. The real power then comes from using LogQL, Loki's query language.
Right.
You write a query to compare error log rates between the Canary and baseline pods.
Ah, so you can see if the Canary is throwing more errors than the baseline.
Exactly. For instance, you calculate the ratio of errors over, say, a 5-minute window. If that ratio jumps above a set threshold, maybe 1.2 meaning 20% more errors in the Canary, the ACA judge applies a penalty to the score.
Okay, so log analysis directly feeds into the score. Makes sense. And Pyroscope, how does that get set up?
For Pyroscope profiling, you usually deploy it either as a sidecar container alongside your Flink Task Manager pods or as a Java agent injected into the JVM. It then continuously profiles CPU and heap usage.
And Prometheus scrapes metrics from Pyroscope?
Yes. Pyroscope exposes metrics like Pyroscope pope seconds total or Pyroscope backup status total. Prometheus scrapes these, giving you that granular performance data for the analysis.
Wow, okay. So you got metrics flowing from Flink and Pyroscopes, logs flowing into Loki and being analyzed, a ton of data. How does the judge boil all that down into that single make-or-break Canary score? What's the logic there?
It's a multi-step process designed to be robust. First up is window alignment. This is critical. You have to compare apples to apples, right? The system uses the timestamp when the rollout started to define consistent time windows, usually 5 minutes long, for both the Canary and the baseline data.
So you're looking at the same 5-minute slice of time for both versions?
Exactly. No comparing morning traffic for the Canary with afternoon traffic for the baseline. Then you define your key metric groups and weights. You decide which metrics matter most. For example, throughput might be 30% of the score. End-to-end latency, maybe the P95 value, another 30%.
P95 meaning 95% of requests are faster than this value.
Correct. Then maybe checkpoint duration, P99 gets 15%. The error rate ratio from Loki gets 15%. And CPU memory metrics from Prometheus and Pyroscope get the last 10%.
So you weight the metrics based on business or operational importance.
Precisely. Now, how do you compare the Canary and baseline values for each metric? You use statistics, specifically Welch's t-test.
Okay, digging back to stats class. A t-test compares the means of two groups.
That's the idea. It tells us if the difference we're seeing between the Canary and baseline for a specific metric, like latency, is statistically significant, or if it could just be random noise. We look at the p-value from the test. A low p-value suggests a real difference. We convert that p-value into a subscore for that metric, usually from 0 to 100.
So each key metric gets its own 0-100 score based on the t-test.
Right. Then finally, aggregation. You combine these individual weighted subscores into the single overall Canary score. That final score, maybe 98 out of 100, is then published as a Prometheus metric itself, like Flink Canary score rollout, your app rollout.
Making it easy for Alert Manager to monitor it.
Exactly.
Okay, the score is calculated, published as a metric. What happens next? How does this loop close automatically from score to action?
Right, the automation flow, it usually kicks off at the initial traffic shift. Argo rollout starts things by sending a small percentage of traffic, say 10%, to the new Canary Flink job.
Just dipping its toe in the water.
Pretty much. Then the ACA judge starts its work. It runs as a Kubernetes job, typically scheduled to execute every minute. It's in this continuous judging loop.
Checking the Canary's pulse every minute.
You got it. In each run, the judge queries Prometheus and Loki for the latest 5-minute window of data for both Canary and baseline. It calculates the subscores, applies the weights, gets the final Canary score, and crucially, it then posts this result back to the Argo Rollouts API, letting Argo know the health status.
Okay, so Argo is constantly updated. What about the rollback?
That's where Alert Manager comes in, monitoring that Flink Canary score metric. You configure an alert rule in Alert Manager, for example. If the Canary score drops below, say, 95 for maybe 2 consecutive minutes, 2 judge runs.
So not just a single blip, but a sustained dip.
Right, avoids being too trigger happy. If that condition is met, Alert Manager fires an alert. That alert is configured to trigger an action, often using a webhook receiver that calls the Argo Rollouts API. It essentially tells Argo, abort this rollout. Maybe via a command like kubectl argo rollouts abort Flink rollout. Traffic snaps back to the baseline,
Preventing a wider problem. And the flip side, promotion.
if the score stays above the threshold. Consistently say it's 95 for 10 consecutive minutes, 10 judge runs, the system can automatically promote. Argo rollouts, seeing the consistently good score or receiving promotion triggers based on it, will gradually shift more traffic, maybe 25%, then 50%, then 100%, fully validated automated promotion.
That's a really smooth automated flow. Initial shift, continuous judging, score calculation, real-time feedback to Argo, and then either auto rollback via Alert Manager or gradual auto promotion. It sounds incredibly robust on paper, but, production is always interesting. What are some common bumps in the road, the gotchas, when implementing this for real?
Oh, there are definitely practical hurdles. You're right. One common one is cold start metric noise. When a Flink job first spins up, especially the Canary, its initial metrics can be all over the place while it initializes, connects to Kafka, loads state.
Right, it's not stable yet, so comparing it immediately might give a false negative.
Exactly. The mitigation is pretty straightforward, though. You just configure the ACA judge to skip the analysis for the very first checkpoint interval, maybe the first minute or two. Let Flink warm up before you start judging it.
Makes sense. Give it a moment to settle. What else?
Out-of-order logs. Sometimes, especially in distributed systems, logs might arrive at low-key, slightly out of sequence temporally. This can mess up time-windowed queries comparing error rates.
Yeah, I can see that. How do you handle it?
A couple of things. Loki has features to handle this better, like using its more robust log parsing filter, which is less sensitive to minor ordering issues. You can also tune settings in Loki Canary, like increasing the allowed out-of-order percentage.
So tune the tooling to be a bit more forgiving of real-world network jitter and stuff.
Basically, yes. Another big one, especially with complex Flink jobs, is metric cardinality exploitation.
Too many unique metric labels overwhelming Prometheus.
Precisely. If your Flink job has hundreds or thousands of parallel tasks, and you export metrics tagged with each task ID, you can generate millions of unique time series. Prometheus might struggle.
Ouch. So what's the fix? Don't track per task.
The best practice is often to pre-aggregate inside Flink before exporting. Instead of exporting records per sec for every single task, aggregate that metric at the job level within your Flink code and just export the job level total or average.
Aggregate first, then export. Reduces the load significantly.
Hugely. And finally, profile cost. Continuous profiling with Pyroscope isn't free. It consumes some CPU.
Right. You don't want the observability to impact performance too much.
Exactly. The mitigation here is sampling. You don't need to profile every single task manager instance. Enable Pyroscope only on a small subset per version, maybe just 2 task managers for the baseline and 2 for the Canary. This usually keeps the overhead well below 1% CPU, but still gives you statistically significant profiling data to catch regressions.
Smart. Profile a representative sample, not the whole fleet. Those are good practical tips. Okay, so beyond the cool automation, how does this actually help the engineers? When something does go wrong or the score drops, how does the system help them figure out why quickly? What's the UX like?
Yeah, that's crucial. The automation is great, but engineers need insight. The core of the user experience is typically a Grafana dashboard specifically designed for Canary analysis. It starts with a health overview, high-level stuff, traffic split percentage, the current overall Canary score. Your first glance tells you if things are okay or not.
The quick pulse check.
Right. Then you'd likely have visualizations like a latency versus throughput heat map. This can help spot performance degradation patterns visually, like is latency increasing only at high throughput? For digging into errors, you'd have an error logs diff view. This uses Loki Explore under the hood to show you the error logs side by side for Canary and baseline, highlighting differences.
So you can immediately see if the Canary is logging new kinds of errors or just more of them.
Exactly. And maybe the most powerful part for performance issues is the CPU flame graph diff from Pyroscope.
FlameRFs visually show where CPU time is spent in the code, right?
Correct. And the diff view directly compares the flame graph of the Canary with the baseline. You can visually spot where the Canary is spending more CPU time, pinpointing the exact functions or methods causing a performance regression.
Wow. So you can go from seeing a score dip to seeing latency is up to seeing exactly which function call in the new code is slower.
That's the goal. The impact is huge. Engineers can often drill down from that high-level bad score to a specific problematic stack trace in, like, under 30 seconds.
That's incredibly fast for diagnosing complex Flink issues.
It dramatically speeds up the whole debugging and resolution process. Less guesswork, more data-driven diagnosis.
So let's talk bottom line. We've covered the tech, the gotchas, the UX. What does this all mean for a team, for the business? What's the quantifiable impact here?
The results reported by teams using this are pretty compelling. First, mean time to detect regressions, how quickly you spot a problem. It often drops dramatically. We've seen examples going from maybe 3 minutes down to just 30 seconds.
A 6x improvement. That's significant in a production incident.
Absolutely. Catching it 6 times faster can prevent a lot of downstream pain. Second, rollback frequency. Because problems are caught earlier, far fewer rollouts proceed to higher traffic percentages before being aborted. You might see something like less than 2% of rollouts ever getting beyond 25% traffic before a bad score triggers a rollback. It minimizes user impact.
Catching almost all issues in that initial 10% or 25% phase.
Exactly. And perhaps the most crucial metric, data integrity. Teams using robust ACA like this often report 0 data corruption incidents since implementing it.
0. That's huge for systems handling critical data.
It really is. It speaks directly to the effectiveness of preventing those silent, insidious failures. So the core insight, the takeaway, is that combining Prometheus for metrics, Loki for logs, and Pyroscope for profiling, all orchestrated by an automated judge like the ACA judge, makes Flink rollouts fundamentally self-validating.
You get the speed you need for modern CI/CD, but also the critical safety net required for these important streaming applications. That really paints a clear picture. Automated Canary analysis isn't just a nice-to-have. It genuinely transforms how you manage Flink deployments, turning risky updates into reliable, self-healing processes. It's a game changer for teams running Flink at scale.
Definitely. And maybe a final thought for you listening. Consider how these principles could apply beyond Flink. This idea of combining deep observability metrics, logs, and profiles with automated statistical analysis. Where else could that be used in your systems? What other critical applications, maybe microservices or batch jobs, could benefit from this level of continuous automated health validation during rollouts? It's a powerful pattern.
That's a great point. Thinking about where else this multi-signal automated approach could bring more safety and speed. Lots to mull over there. Hopefully you picked up some useful insights and maybe an aha moment or two for your own work. It's all about making deployments faster, safer, and, well, smarter. That's all for this deep dive. Thanks for joining us.